Let's talk about friction. Typical questions of this type of problems are when we have a box like the one shown on the left hand side, and that force is being pushed by a force F, and we are interested in knowing, for example, what is the force required to move that box, and we're interested to know whether the box will tip or the box will slide. Tipping is basically moving as a rigid body in the end of the box, and sliding of course is sliding of the box. Now, to be able to analyze this type of problems, what we need to do is go back and study a little bit about the concept of friction. And if you have taken physics in the past, you might have seen that the friction force, and a question that might be stuck in your head is, a friction force is equal to the normal force times a coefficient of friction. And we're going to see that that is part of the concept of friction, but not the whole thing. If you're not taking physics, no problem. I'm going to explain everything in here. All right, so when we look at a friction force, and let's say that we're talking about a friction force here at the bottom, right, at the bottom of this box that is being slid or trying to be pushed with that force F. So that friction force, if I do let me make here a title, friction force. And if I do a diagram, XY diagram, right? And in this vertical axis, I'm going to put my friction force. I'm going to call it Fr. So this is friction force. Let's call it Fr. And in my x-axis, I'm going to put my force F that is pushing that force, that box, right? What we're going to see is that the friction force at the beginning cannot be more than the force pushing the box, because otherwise that means that the box will move in opposite direction in which the force is being pushed, which is not physically possible. So at the beginning, those two forces are going to be the same magnitude, and they're going to push against each other, right? It's a static equilibrium. So because of that, we're going to have something like this. Now we reach a point where the friction force is not strong enough to be able to hold the pushing force. And in that case is where we're going to find that the friction force is the coefficient of static friction times the normal force, right? So that's the point. This particular point over here is when that equation is true. Then after that, the friction force goes down a little bit, and then we have my dynamic friction force, and that becomes constant. So even if I push harder, I'm going to find a force pushing back, which is that dynamic friction force. So in this part over here, we have that my friction force is going to be equal to a dynamic coefficient of friction times my normal force. At this particular point, that point, it doesn't mean the whole curve, right? At this particular point, I'm going to find that my friction force is going to be my static coefficient of friction times my normal force. And overall, in the rest of the curve, we're going to have that my friction force is going to be, put capital R, be less or equal my mu s times n. And this is the equation that we're going to be using. So we're gonna recognize that the friction force can be less than that maximum point, right? We're gonna recognize that. Okay, very good. So when we're looking at those blocks like the ones shown on top, right? This one in here, we can do a free body diagram to be able to analyze that system. And to be able to do that free body diagram, what we can do is something like this. So my free body diagram is going to look something like this. I'm going to have my box. I'm going to have the force that is trying to move the box. We're going to have the mass of the system, and what we're going to do is we're going to find the center of mass, and we're going to put the weight of that box right there. Often the assumption is that the center of mass is in the centroid of that shape. And then now we need to start looking about the friction force and the normal force. If I try to do a somewhat realistic drawing of that normal force, we're gonna realize is by me pushing that box, at the bottom we're gonna really have a distributed force. And that distributed force is going to be less in the location where I am pushing the box and more at the other end, right? That's really what's happening. As I push more, that left-hand side gets smaller and smaller and smaller to the point of the limit, which is where all the normal force is in this end, of the box, right? It's the bottom right end of the box. And then in addition to this, we're going to have our friction force. I'm going to draw it a little bit longer than the bottom just to make the point that force is right there, right? That's going to be my friction force. Now, I can look at an equivalent point load of that normal force. And what we end up having is something like this. We're going to have my force pushing on the box. I'm going to have my weight, my friction force, and now I'm going to have my normal force, but because it's in the center of that shape, it's going to be a little bit towards the right, right? A little bit towards the right, and that distance might not be known. The location where that force is, that distance, might not be known. Okay, so we're going to have two main assumptions when we try to do these free body diagrams. We're going to either, when we look at a problem, we're going to try to do an assumption that the box is either sliding or that the box is tipping. And the shape of that free body diagram, or the way that the places where we put the forces, is going to depend on that assumption. And there is no way whether or not a box is sliding or tipping before we actually solve the problem. So we have to solve these problems, we have to make an assumption and then go through those assumptions and see at the end whether or not my answer is correct. So we need to check our assumptions at the end of the problem. So how does that work? Well, let's just start with the free body diagram for sliding. And for that sliding, we're gonna have, let's see, you're gonna have my box right here. Let's make the assumption that's my box. Let's say my force that is pushing is somewhere over here. I'm gonna have my weight, right? No difference on those two forces. And let's see. And that's supposed to be a W. And then we're gonna have, when we have sliding, where that normal force is not all the way to the right hand side, right? So we're gonna have that the normal force is going to be somewhere in here, right? And if we label this distance between the center of the box and the normal force, let's label that X. That X is going to be unknown, okay? And we also have our friction force. Let me change the color so we can see that friction force a little bit easier. So I'm gonna do my friction force. It's going to be applied right there. That's going to be my friction force. So that's going to be the free body diagram when we're looking at a sliding box. And the equation that we need to use for that is, since we are sliding, or better yet, since we're looking at statics, we're gonna be looking at this particular point over here, right? Let me do it circle in red right here, this particular point over here. In dynamics, you will see the rest of the curve, but right now we're looking at that particular point over there, right? So this is the point of sliding. This is when it starts sliding. Right? So because it is sliding, what's going to happen is we're going to add one more equation that we can use. And that equation is that the friction force is equal to mu s times n. Mu s times n. And when we solve for unknowns, our unknowns includes x. So we might have to solve for x. In most cases, we're going to have to solve for that distance x. And the check that we can do is we need to check that my distance x is less or equal than b over 2, where b is the base of that box, right? So b, let's say that box, that's going to be b. Okay? If x is more than b over 2, what that means is that the normal force is going to be outside that surface, which is physically impossible. And what that is going to tell us is that the box is not really sliding, but it's actually tipping. And as I said at the beginning, there is not really a way to know which way to go, either it's sliding or tipping. You're just going to have to try one of those first, and if it doesn't work out, go and solve it for the other way. All right, so what is the free body diagrams, typical free body diagrams for tipping? So let's start here. And what we're gonna see is we're gonna have our box. No difference in our weight and in the force that is pushing that system. And what we're going to see is now that we actually know the location of the normal force, right? We know that because it's about to tip, right? It's about to tip. The normal force needs to be at the very end, right? What does that mean? Well, that means that distributed force that I did on the top free body diagram, it basically got reduced to a single force at the very end. I mean, think about it. If you're tipping a box, eventually it's going to get to that edge of that box. So the normal force needs to be there. And our friction force, I'm going to make it red also because so we can able to say the friction force is going to be right there. That's going to be my friction force. Now, in this particular problems, what we're going to find out is that our equation for the friction force is going to be different, right? So the equation for the friction force is that friction force is less or equal, well, less than, right? Mu s times n. So we're not developing the full static friction force. What that means is in this top left diagram, in this part on here, on this straight line, is when we have the tipping, right? So it's somewhere in there, somewhere in that straight line we have tipping. All right, so the unknowns, in this case unknowns, to solve for with our equations of equilibrium include that friction force. By the way, the friction force is also an unknown in the case of sliding, right? We have one more unknown, which is x, but we have also one more equation, which is that Fr equal to mu s times n. On the right-hand side, in the free body diagram for tipping, we're not going to have that additional unknown of x because we know the location of the normal force. And the way to check way to check this is to make sure that friction force is appropriate, right? So that friction force is less or equal mu s times n. So in a nutshell, what you want to do with this type of problems is choose one of the two. If it's tipping, you go with the right hand side free body diagram, solve for your unknowns, and then do the check. The check is absolutely necessary in that case. And the check for tipping is that the friction force is less than mu s times n. If you assume that it is sliding, then you go with the left-hand side free body diagram. You need to solve for that x, in addition to any other unknowns that you might have. And then your check is that your normal force is under the box, so that the x is less or equal to b over 2. If that's the case, then you have solved the problem. If your checks do not work out, is because your initial assumption was incorrect, and you need to do the other free body diagram and solve for the unknowns using the other set of equations.